Dear viewers, I hope that you are all fine. This is Dr. Tasadduk and you are watching Bohr-bury Educate. This section is chemistry and today's topic is Pauli's Exclusion Principle. I urge you all to subscribe to get the latest uploaded content on Bohr-bury Educate. Let's move forward towards today's lecture. In around 1925, Wolfgang Pauli, who was an Austrian physicist, put forward this exclusion principle. This is a quantum mechanical principle originally put forward for atomic particles that have either a plus 1 by 2 or minus 1 by 2 spin. That is the half integer spin. The atomic particles like fermions, which includes electrons, quarks and neutrinos, follow this rule, while as the other atomic particles known as the bosons don't follow this rule because they have integer spins. Since we are dealing with the electronic configuration principle here, we would refer to Pauli's statement for electrons, or in other words, extend this exclusion principle to the electrons. So the principle states that no two electrons in an atom can have same set of 4 quantum numbers: principal quantum number L, azimuthal quantum number L, magnetic quantum number M, and the spin quantum number S. This means that at any instant only 3 quantum numbers can have the same values or can be same, while as the 4th quantum number has always to be different. In other words, electrons with the same spin here can never exist in the same orbital. Rather, they have to have opposite spin or different spin quantum numbers, that is plus 1 by 2 and minus 1 by 2. That means the quantum number, that is the spin quantum number, can be either plus or minus 1 by 2. This means that the particles or the electrons in quantum mechanics that possess half spin exist in anti-symmetric state. So in anti-symmetric state there is always low energy, whereas in case of the same spin there is always high energy, and high energy is not favored in case of the atomic orbitals, and the electrons will always follow the low energy or more stability rule. Now let's take an example to understand the Pauli's exclusion principle. If I take the Bohr's orbits, that is K shell, so in case of K shell, that is the, for example, we can take it as 1s orbital. In that case, for K shell, n is always equal to 1, while as the azimuthal quantum number is always 0 and the magnetic quantum number is also 0, while as the spin quantum number is going to be plus 1 by 2 and minus 1 by 2. In this case, you can see all the 3 quantum numbers here, that is n, l and m, they are same, while as the 4th quantum number, spin quantum number, is either plus 1 by 2 or minus 1 by 2. That is, the 4th quantum number is always different. Let's extend this exclusion principle to the L shell now. So in case of L shell, what we have is the n is always equal to 2, the azimuthal quantum number L is always equal to 1, and the magnetic quantum number has 3 different values, that is 0, plus 1 and minus 1, while as the spin quantum number can have 2 values, that is plus 1 by 2 or minus 1 by 2, and this is going to be same. Now if I try to combine all of them by using the single magnetic spin quantum number, so we get these following combinations. There will be a total of 6 different combinations for the magnetic quantum number in this L shell for the plus spin and the minus spin. So let's look at all the 6 different combinations. So the combinations are going to be, n is going to be 2, L is going to be 1, and we'll take 0 for plus 1 by 2, so m is going to be 0 and this is going to be plus 1 by 2. Again it's going to be 2, 1, then taking the other 0, 0, and the spin quantum number is minus 1 by 2, so this is one set. Similarly, n is going to be equal to 2, this is going to be equal to 1, and then we'll take the plus 1, and we'll take here plus 1 by 2. Then again taking the plus 1 for the minus 1 by 2 spin, that is 2, 1, minus 1 by 2. This is the other set. Similarly, there is going to be third set, that is 2, 1. The third set is going to be for minus 1, that is 2, 1, minus 1. and plus 1 by 2. Then 2, 1, minus 1 and minus 1 by 2. The spin quantum numbers are here different. Again, the fourth set is going to be 2, 1, and then it's going to be 0 plus 1 by 2 and 2, 1, 0 and minus 1 by 2. So in an overall we get 1, 2, 3, 4 different sets, and in all the 4 different sets, if I try to adjust the electrons, we'll see there are going to be 2 electrons in this shell and 2 electrons here, 2 electrons here, 2 electrons here. One electron will have the plus 1 by 2 spin, the other electron will have minus 1 by 2 spin, similarly in these 3 cases. Now since this is the L shell, that means we are going to have to adjust the electrons in 2s and 2p suborbitals. But since 2p has 3 suborbitals, that is 2px, 2py and 2pz, 2 electrons will go in each of the suborbitals and a total of 6 electrons will be adjusted in the p suborbital. So out of all these, that is 8 electrons, here will be 2 electrons, a total of 8 electrons have to be adjusted in the L shell. 2 electrons are going to be in 2s subshell and 2 electrons in 2px, 2 electrons in 2py and 2 electrons in 2pz subshell. So all the electrons are distributed, that's total of 8 electrons. However, you can see that in each of the subshells or the suborbitals of the p orbital, you can see the electrons in each case have different spins and the quantum numbers, that is the 4 quantum numbers, are different. Even if you have 3 quantum numbers same, as you can see in all of these cases, all the 3 quantum numbers are same. These all quantum numbers are same in each set. However, the 4th quantum number is always going to be different. Now, if we look at the application part of the Pauli's exclusion principle, it not only aids in the electronic configuration of the atoms, but also explains the semiconductor behavior and the ordinary matter as well. This concludes our lecture. I hope you guys enjoyed it. Also, your comments mean a lot to us. Please do subscribe for our latest videos and hit the like button. Until next topic, take good care of yourself. Bye.